So let me invite to the stage the first speaker, Sam Stevens.
It is. Oh, wow. Shocking. Okay. All right. So my project was on the interaction of electrons in single-walled carbon nanotubes with sp3 defects described by the Slater determinant. I guess a little bit of background on what you'll be seeing, and I can show it in a photo, is the defect that was used was aniline at 5 different spaces. The two we're going to be looking at is a single bond length away, and then at 2.5 nanometers away. So when looking at the first figure here, some important notes to make is that this blue line, I guess, I don't know if on the Zoom, if they can see what I'm pointing at with the laser pointer, but for the bottom figure, the blue kind of like the blue line is the potential as you go across the carbon nanotube. And if you notice, as you get closer to your defects, your potential increases. You also can see like an orange and a yellow line right here. This is going to be the eigen function offset by the eigen energies. This distance right here also indicates that there is some optical activity within the carbon nanotube with these defects. We can take a look at the second figure here and see that due to like as the distance increases, that separation outside, like away from your like defect itself, has very minimal separation. Another thing that we can note as well is as you, okay, I think the top of the figure is kind of cut off, but you have two kind of like different colors. They're probably not very easy to see on Zoom or maybe at a distance, but as you like go up on your potential towards the positive, those are just higher eigenstates. I think that's everything on that. And then I guess when you just compare, yeah, like right here, like as you get closer to 0, your eigenstates get higher and higher, and you can kind of see it really well at the top 2 here, as those are just 2 higher eigenstates. Do you want me to, I think you have access to that. And continuing on, so I guess kind of what I was just talking about, you can see the higher eigenstates, the eigenfunction, which is offset by your eigenenergy and your potentials, and then just comparing our single bond length away in 2.5 nanometers. You can see that at the 2.5 nanometers, your potential is, I'll call it prettier, and it's kind of easier to see. It's a lot more like congested, and like you have one single peak at each of the carbon or the defects for your 2.5 nanometers, while you have kind of like a set of 4 at the 1 bond length. So now getting into the math and I guess more the work of what I was trying to get at. So when looking at the single bond length away, we have our eigenstates of 1 and 2. We have what is known as the Hartree product, which is, oh, maybe I didn't. So the Hartree product is basically just when you have your eigenstate, or the wave, I believe it's the wave function of your eigenstate 1 times the wave function of your eigenstate 2, subtracted from when you flip your eigenstate, or your eigenstate 2 and 1, or particle 1 and 2, being denoted by x1 and x2. When those eigenstates get flipped, the difference comes out to be the Slater determinant, which is shown by this equation below the third figure on the right. And then just same thing here, except it's at the 2.5 nanometers away. I think, oh my God, nice little thing about this figure, I think this one just shows it a little better of how, like, you have, this is 0 is the yellow. I don't know why it's green over here, but yellow is 0, and then when you subtract it, this becomes positive because the blue is negative within these figures. This, I think, shows it a little more, like, shows it, but I think that it doesn't show it as well as this figure. So getting into, I guess, the results based on what our Slater determinant shows is as the defect distance increases our Coulomb potential, which is shown by our equation right below our the graph right here. These are the same, just one I think visualizes it a bit better. It uses our Slater determinant and Slater determinant, and then did I not put that equation on there? Maybe I didn't. But yeah, so Slater determinant, and I believe that's the Hartree product. And then, as we can see, as the distance increases, our potential decreases, and between the first two defects, there's a pretty significant potential decrease compared to as the defect distance increases. And then I guess leading into my last figure, which is changing the eigenstate value to 1 and 4 when comparing. This is the just Slater determinant. You can see that it's a lot. Oh, I should say this is also at the 2.5 nanometer distance. So compared to the 2.5 right here, there's a lot more going on in the figure. And what I hypothesize from this is that as you have these alternating positive negative functions along the x and the y, I believe that is we have the fourth eigenstate compared the potential difference between eigenstate 4 and 1, and then as you kind of go farther down the x-axis, I believe this is 3 and 1 and then 2 and 1. That's what I've hypothesized on it. I kind of ran it out of just to see kind of how the Slater determinant would and the figure and potentials would look different. This is the potential energy that would come out of it, which is the number that you would have here with your Coulomb potential, and you can see that it increased as your eigenvalue is different, and that's it.
Okay,